Hi, welcome to TD2, and this TD will be part of a Python series for the semester, with the second one being machine learning using Python. I'm your director of IT, Tina, and before we get into coding using machine learning, we first have to understand some concepts about it. What is machine learning? Well, machine learning learns from analyzing data and statistics and uses data analysis to predict the outcome. How it differs from traditional programming is that in traditional programming, when we write the code, we write it to get data and then implement rules for that data. When we go to input values, code runs when the inputted values and previous data, references the rules, and then provides output based on the two. So for example, if we program a ball game where if the ball hits the tile, the ball should bounce back and then the tile should just disappear. We need pieces of data like the location of the ball, the location of the tile, and implement rules like if the ball collides a tile, then the tile will disappear and then the ball will bounce back from the collision location. The answer the program comes up with is the response to these data and rules. So for machine learning, it uses the same variables, but just in a different orientation. It will instead get lots and lots of data with answers already given, and then figure out the rules that connect each data and answer together. So for example, you can feed a model tons of examples of people expressing different emotions and then labeling the correct answers along with it. The machine would then define key rules that would distinguish each into a category so that when you feed it a new unfamiliar example, the model will be able to predict which emotion it believes it should be. Now before we move on, I use some terms that you probably aren't familiar with, so let's just go over some of the basics. Labels are variables we're trying to predict. They can be more than two labels, and it's part of supervised learning, which we'll get into. An example is just one piece of data. Features are input variables that describe that data. There again can be multiple of these, like spots for a cheetah and stripes for a tiger. Just any defining attribute that the computer can use to distinguish between the two. A model defines the relationship between features and labels. Again, an example is just a particular instance of data, which can be an image of a cheetah we feed into that example, or that model, I'm sorry. Labeled examples have both features and labels defined as x and y variables that can be used to train that model. An example would be spots as a feature and cheetahs as a label. Unlabeled examples are the opposite of that, which only has the feature but not the label that can be used to make predictions on new data. So you can see in the example, we have the feature stripes, but not the label, which would have been tiger. This is unsupervised learning so that the model can figure out that label on its own. Models map examples defined by learning internal parameters to predict labels. They're what we're trying to build, so machines that are capable of learning how to predict an outcome with data it's fed. A regression model predicts future continuous values or labels. This is usually done linearly, and we'll only do one of these since I think personally charts and plots are kind of boring. So this is just a diagram of the terms that I went over just now. So features are fed into models, and then models make an inference or a prediction, and then it'll compute the loss to see if how accurate their prediction was, plus or minus, and then go back to compute that parameter updates to the model to make better optimized predictions. And then labels go into the compute loss to tell this model if it was off or not, and how much it was off by. Foundation models, instead of predicting continuous values like regression models, instead they'll predict discrete values. It'll take examples already categorized into a data set and train on it to find a relationship between the two, hopefully to be able to predict the category for new data. An example of this is something you may already be familiar with, which is just email spam filtering, where it predicts email contents into either categories spam or not spam. Loss is just the square of the difference between corresponding prediction, and the corresponding label. It's calculated by subtracting prediction from observations and scoring the output. We'll use this loss in our coding. Don't worry too much about this since it would just be a line we type. Same thing with mean square error. Mean square error is average square loss per sample over the whole data set. So how off the prediction was plus or minus. I touched on these terms a bit earlier, and so supervised learning trains on many examples and attempts to find a model that minimizes loss. It does this by using labeled data to train the model and direct feedback to make more optimized future predictions. An example of this is a linear regression model, which we'll be making one inside an upcoming exercise. It will determine how the input predictor variables affect the output response variables. You'll see what I mean more when we get into the exercise. But unsupervised learning is learning with unlabeled input data, so the opposite, without guidance and no feedback, to try to find hidden structures and data to link the data together. A good example of this is k-means clustering, where there's no given labeled data for clustering. Reinforcement learning is reward-based that learns based on feedback and adjusts based on that feedback. Its ultimate goal is to maximize rewards or positive feedback. An example of this is natural language processing, where we teach an agent how to generate or classify text by labeling and giving feedback accurately on accuracy. Variables, the model makes predictions or forecasts based on input data or the X variable, and it then analyzes historical data and learns its patterns, which can then be used to predict future outcomes or trends. An example of this can be the amount of sunlight a plant receives. And for responses, it's the Y variable, and it's the output that is dependent on the predictor variable. So same example, subject is a plant, and the response variable could be linearly related to the amount of sunlight it receives, and that would be the height of the plant. And finally, for definitions are hyperparameters. Hyperparameters are just parameters that can be fine-tuned and adjusted, which then increases the accuracy score of a machine learning model. An example of this we'll see later in exercises is the filter size in convolutional neural networks. Machine learning. Machine learning is a step towards AI or artificial intelligence. It can solve problems we wouldn't possibly be able to comprehend mentally, and so computers are a great way to tackle that issue. It's almost more like a science, a natural science, than a mathematical science, since we make observations, we run experiments, we use statistics, and we analyze those results. For machine learning, you need a firm foundation of three things: coding, of course, math, and machine learning theory. Don't worry, I won't make you do heavy math in this TD, but I will go over some machine learning theory and, of course, how to code a machine learning model. So some real-world applications of machine learning are some you've probably already encountered before or use on a daily basis. Products like Amazon's Alexa or Apple Siri can schedule an appointment or play music at request by inputting your request as data, decoding it using neural networks, and then providing that output to you in the form as playing a playlist. Google Maps or Apple Maps can predict commute times by categorizing areas of your route into either clear or slow moving or congested. And then by taking average time taken on specific days at specific times on your route and combining it with real-time location of data of vehicles on the road, it'll be able to give you the prediction for commute time. And finally, for email spam filtering, it can sort and categorize email contents to classify them as with spam or not spam, where spam or not spam are the labels, and then attributes like the email header or the to or from address are features. So in order to understand the code in the first exercise, or some of the concepts that we'll be using throughout this TD, you have to have a basic understanding of neural networks. So in this diagram, each of these columns of circles are called layers, and each of these circles are called neurons. So the connections between each of them are called dense layers because of the dense connectivity between them. A dense layer is just a simple layer of neurons, where in each neuron receives input from all the neurons in the previous layer. We can then train these neural networks to predict the rules of data and answers through probability, and then we'll see this in the exercise later on. Okay, that's all for the intro.